All right, let's talk about wireless. If you don't know who I am, I'd be very surprised. But hi, I'm Dan. I'm the tech lead. I do the demos, and I also run the wireless interest group that we call Wiggles. So a lot of this stuff is from stuff that I learned and I teach in there. So if this interests you, we meet from 5:30 to 6:30 every Thursday. Yeah. Okay. So on that topic, who am I? I'm Dan LaChance. I'm a second year CSEC major. I'm working on a CE minor. Um, I love going climbing. Sadly, I won't be there today. I got a birthday dinner. And then obviously I love Wiggles, Wireless Interest Group. And then this summer I'll be working at Microsoft. And if you need me, there's my email. So let's get started. What is a wireless? So wireless is just light. It's just lower frequency light, and it transmits on those specific radio frequencies. As you can see, the visible light spectrum is all the way down on this end, so almost ultraviolet light. I'm sure you've heard that all the time. That's just really, really high frequency radio waves. And then everything below that, pretty much like 100 gigahertz and all the way down to like 1 kilohertz is all used for wireless communication. So that's like your AM radio, FM radio, just cellular, anything that communicates some sort of data through the air. Yeah. Okay, so the basics of this and how this actually works is, so all of these waves, as you may know if you've taken a physics class, light propagates through electromagnetic frequencies. So these waves travel and they have counteracting forces that work perpendicular to one another, and they propagate infinitely. So they move at, you guessed it, the speed of light. So wireless communication is extremely fast for that reason. And then the way you calculate some of this stuff, there's you can go from like wavelength to frequency. It's an inverse relationship where c is the constant for the speed of light. And then frequency to periods, just the amount of time that one period completely takes. So then, yeah, amplitude, wavelength, just the amount of time it takes to propagate once. I'm sure you've heard of almost all of that. And this is what it actually looks like. So you have the magnetic field and the electrical field, electromagnetic wave, EM, and those are acting orthogonally, so perpendicular to one each other. And if you've taken a physics class, you know the right-hand rule. So if you have an electromagnetic field and or if you have an electric field and a magnetic field in those two directions, then like my thumb is the magnetic field, and then the electric field is my 3 fingers, and then the velocity is the direction that it's going to be moving, and that's my index finger. So yeah, that's how light works. Pretty cool. So when you're working with wave propagation, there's a specific range that all of these signals can propagate and still hold their expected value. And so it depends on a lot of factors, but the main ones are like how much power you use to transmit the signal, the distance to the receiver from where you're transmitting from, the frequency, because higher frequencies don't propagate as far. So that's why we use high frequencies like 2.4 gigahertz or 5 gigahertz for Wi-Fi, because you can pack a lot more data into it, but it's not going to travel as far. So, I mean, if you walk 50 feet away from a wireless access point, like in your house, like a router in your house, then you're not going to be able to connect to it anyway, and that would be why. So then, the reason for that is because the received signals have to be above the noise floor. So generally, it's like 15 to 20 decibels above that noise floor is what you want to be in order to get a good signal. If you're at the noise floor, you're not going to hear anything, and if you're any less than like 15 or 20, it's not going to be clear, and you're going to have a lot of static. Yeah. Okay, so you can predict how much power you're going to that your receiver is going to receive the signal at just by the free space path loss function and the receive power function. So basically it's just math. Just input your stuff into that equation, like how far are you from it, what's the wavelength, and then how much power and what's the gain of your receiver and transmitter. Yeah. Okay, so how is data actually transmitted on specific frequencies? So every signal, say you have this signal, that signal clearly is not working at a high enough frequency. So you need to modulate it with a carrier signal. And so amplitude modulation is one of those. And this is what it looks like. So you have your signal. You change the amplitude based off of, you change the amplitude to kind of encode that signal. And then for FM, you change the frequency. So you can, there's also like most modern radio frequency is digital, so it's packing zeros and ones in a whole bunch of different kinds of modulation schemes. There's like that whole diagram up there if you're interested. But really all I'm going to talk about is the analog data, so AM, FM, and PM. But yeah. So speaking of, those are the three that I just mentioned. So amplitude modulation, that's where you're changing the amplitude to encode your zeros and ones. Frequency modulation, you have like a period where for zero, you have a period where it's, say, 100 megahertz. And then the next period, it's 110 megahertz. And the first 100 megahertz for one period is a 0. 110 megahertz for the next period would be a 1. So that's how you can encode binary data. And then phase modulation, PM, this is where it gets a little bit more complicated because you're changing the point in, like think of the unit circle. So you're changing the point in the unit circle at any given time period. And it will end up looking something like this. So say your 1 is where it starts at -1 for your time period, and then your 0 is when it starts at +1. And so this would be 0, 1, 1, 0, 1, something like that. Cool. Okay, so transmission rate. How much data can you transmit in a second? Well, that depends on the baud rate, which is the bit rate times the number of bits per second. And the way you figure out the number of bits per second is just how many combinations there are of, like, say, frequencies or phases that you can do. So phases, it gets very, very large. I've seen schemes that get up to like 16 phases. So you can then encode 4 bytes at a time in like every single second, which is really a lot. Other than that, though, you can just do, say you have 2 frequencies that you're encoding on or you're modulating on. So if you have, say, 100 megahertz and 110 megahertz, that's just a 0 or 1, so that means that your number of bits per baud is only just 1. Sweet. Okay. General RF stuff. So software-defined radios, these things are awesome, and the difference between them is that they pack a ton of what would be hardware for the demodulation into just software programs. And they're generally pretty cheap. Like you can get an RTL SDR for only $35. I checked on Amazon when I was making this presentation. It is still $35, but it goes up by like $5 a year since it's in such high demand. So SDRs are the easiest way to enter the radio world because you can just like boot up a frequency analyzer and then you can just like view what radio stations like actually look like. So you know how you have like you're tuning your standard radio to like 102.9 FM. So if you're listening on that specific signal, that means that there's a station somewhere near you that's transmitting all of that data to you, and then that a standard radio uses hardware to demodulate those signals, an SDR uses software. So pretty simple. So there are three kinds like that I wrote down. These are just three examples. So there's like the really cheap ones, and a good example of that is the RTL SDR. Then there's like the mid-range ones where you can have like get all the way up to like 6 gigahertz. An issue with the RTL SDR is it only goes to 1.7 gigahertz, and the sample rate isn't very large. So one, like Wi-Fi is on like 2.4 gigahertz or 5 gigahertz. For one, you can't even read that high in gigahertz. You can't demodulate those signals. And two, the sample rate isn't large enough for you to actually view packets. But if you have something like a hack RF, you can get up to that like higher gigahertz range. But again, you don't have the same sample rate that you need in order to do like a full analysis of like a Wi-Fi network and the blinking. In order to do a full analysis of a Wi-Fi network and actually view all of the traffic, demodulate the signals yourself, kind of unnecessary, but a good example to explain this point, you can use like a USRP, very high-end, very expensive, but you have huge sample rates and you can view pretty much the entire 2.4 gigahertz Wi-Fi spectrum at once. So, yeah. And then if you don't know of what half duplex versus full duplex means, half duplex just means that you can transmit and receive, but you can't do both at the same time. Full duplex means that you can transmit and receive at the same time. So like a good example of an SDR is a Pluto SDR, one that has full duplex, and it's only like $400, I think. And so you can transmit and receive at the same time. The RTL SDR, you can only receive. And a note on that, too, with the FCC guidelines, Federal Communications Commission, you need to be certified in order to transmit. So please do not do any like unauthorized transmitting on like stuff that you don't own, stuff that's not FCC certified. Like if you have a Wi-Fi dongle and you're transmitting on a network that you own, that's completely fine, completely legal because it has an FCC ID, you're using it for its expected purpose. But say you take an RTL SDR and you're like spoofing GPS, you're transmitting packets in order to make like a phone, think that it's in a area of the world that it's not actually, that is questionable, and if you're going to do that, it should be done in like a Faraday cage. Luckily, we have one of those here. So let's talk about some tools, some things that you can use. So there's spectrum viewers. That just lets you view like specific, the actual signal, so you can see the wave actually propagating. And Spectrum is a good tool for that if you want like an in-depth analysis, but Audacity works well enough for most people because I mean, you're not doing these crazy, like save that for when you have a job. Then general SDR applications, SDR++, my personal favorite. That's just like a frequency analyzer that I'll talk about in a second. Same with SDR Sharp, GQRX. And then GNU Radio Companion, it's a very, very powerful, easy to use tool, and it looks like this. So you can do like pretty much anything with an SDR with GNU Radio Companion, and it's basically just a way of connecting blocks like you would in Scratch, and then all of that just gets translated into Python, and then your Python code runs every time you run a project from here. So what is a frequency analyzer? That's a good question. So if you want to see what signals, like what stations are around you, you can boot up a frequency analyzer like my favorite, SDR++, which this is, and any of those peaks where there's like a really strong signal, that's how you know that there's a station there. And that up there is the fast Fourier transform plot. Don't worry too much about what the fast Fourier transform is, but pretty much what it's doing is it's telling you how strong the signal at each of those specific frequencies is at any given moment. So if you see a peak, like very high peak in like a 20 or like I don't know, probably 2 megahertz sample range, that probably means that there's like a radio station there. So if you're tuning to like I said, 102.9, just like a random FM radio station that I came up with, or whatever RIT's is. Does anyone know RIT's radio station? 89.7. So when you're tuning to 89.7, you're tuning to one of those peaks and you're demodulating all of those signals and then translating it to audio. So that's really what you're doing there. So there's your fast Fourier transform plot. Then there's also the waterfall. So if you want to know, you miss a signal on that fast Fourier transform plot at any given moment, but you want to see where the signal was, that's what you use the waterfall for. So the waterfall keeps it's kind of like a record of the past minute or so of communication. So whenever SDR++ is running, you'll see the fast Fourier transform plot updating like every, 5 times a second. And then it will be like a waterfall going all the way down. And so like 5 seconds ago would probably be somewhere around here. And if there was a signal that was 5 seconds ago, you're trying to see if it's going to transmit again, you can tune to that frequency and then pay attention to the FFT plot again. And then on the side, all of your settings. And yeah, you can do a ton of stuff. You can turn up the gain. You can set squelch so that you don't listen to the static, because who wants to hear the static? You only hear a signal when it reaches a certain threshold. And you can also take recordings. You can save frequencies for later, that kind of thing. And then finally, there's your current frequency all the way up at the top there. And you can tune that. There's like up and down arrows for each of those digits. And say you're going to RIT radio station on what was it, Krish? 89.7. So you could tune that number to 89.7 to listen to your favorite radio station. So some pretty cool tools. This is probably where it gets really, I think it gets really cool, because this gets into like the reverse engineering aspect of wireless security. So there's digital signal analyzers. The only one that I've really touched is Universal Radio Hacker. And with Universal Radio Hacker, it demodulates some of the signals for you, and then you can view the signal strength for each of those. And this is an example from Sammy Kamkar, I would highly recommend checking him out. He's a very good security researcher in the wireless field. And he did this lab pretty much, or like experiment, I guess you could say, with a garage door opener. So there's a 10-bit garage door opener. And every time you hit it, it transmits just this binary. So if you're listening to that specific frequency and you see like big blob, smaller blob, big blob, smaller blob, it's pretty clear what that signal is transmitting. It's just binary. And so that binary actually correlates exactly to what the clicker has. And if you have that clicker, or you just like buy a new one, you can set the clicker and then just like open the garage if you want. But not many garages still use this, so like don't even try to go out and do this for ethical reasons, and it won't work. But just a good example, good case study. So then there's also signal identification. If you're, on a Sunday afternoon, if you just sat down and you're just scrolling through all of the channels on your SDR, on your favorite frequency analyzer, SDR++, and you go on to a frequency that you is clearly transmitting a signal, but you don't know what it is, you could go on to SIGWiki and yeah. Then for specific uses, there's SatDump and Chase Mapper. Yeah, I already talked about that. Don't gotta go into it. Okay, so in Spectrum, I know I mentioned this before, but it's pretty similar to just Audacity. But you can do a little bit more with it, and you can actually set up your own wave and then compare it to the wave that you captured. So you can tune it to be able to transmit the same signal and just use it for like a replay attack. It's pretty cool stuff. Okay, time for the main event. What you all came here for, Wi-Fi. Oh yeah. So what is Wi-Fi? I would hope that many of you do know this, but if you don't, Wi-Fi is pretty much just like the equivalent to Ethernet, just without cords. So this is like a LAN network down on the bottom, and then a Wi-Fi network. So all of these are happening, the laptop, PDA, Wi-Fi phone, they're all connecting to the wireless access point. That's what this is called. It's an access point. So they're all connecting to the wireless access point instead of like a Ethernet gateway. So instead of like a switch. Wireless access points function pretty similarly to a switch. So if you have taken any of the networking classes where you work with switches, it's kind of the same thing, but obviously they do a little bit more since they have to have some sort of encryption. So yeah. Oh, well, I should say also, if frames are not encrypted, I could just like go sit on the other side of the room. The reason that frames have to be encrypted for this, for security reasons, is because it's basically just a transmission. So it's a wave transmission from, say, here to the access point on the ceiling. And there's nothing saying that somebody else in this room can't just like sniff that traffic, since it's just pretty much being broadcasted to the entire room. Just the only place that actually is going to be able to decrypt it is the wireless access point. So yeah. So Wi-Fi 802.11, if you know anything about Ethernet, 802.3, fairly similar, but this came out in 1997, so well after Ethernet. And it operates mainly at 2.4 gigahertz and 5 gigahertz. There's some stuff on 6 gigahertz, but really not used that much, so it's not really worth going into. So there's a ton of different versions, Wi-Fi 4, 5, 6, 7, and then like ABG, AB, there's just like tons of versions for Wi-Fi, and they all have different kinds of encryption schemes and different key standards. So speeds and reliabilities are getting faster. Okay, so 2.4 gigahertz Wi-Fi. So this is what's mainly used. Most people use it, and it mainly works on channels 1, 6, and 11. It works well enough, and there's enough channels so that there's not really that much interference. So it works pretty well. And so there's a consistent 20 megahertz bandwidth for everything, no matter like how much data you're transmitting. And yeah, 802.11, BG, and N all work on 2.4 gigahertz. And there's all of the 13 channels, and that's just like 2 diagrams for all of the channels, and so you can see if there's overlap. Because if there is overlap, there's going to be radio frequency interference. So since they're waves, there can be constructive and destructive interference. Both of those will mess with your wireless signals. So that's why the main standard is to use channels 1, 6, and 13. So I'll go back here. As you can see, it's not only 2.4 gigahertz on the bottom. Should have mentioned this earlier. It's 2.412 to 2.472, and a little bit, obviously, 10 megahertz above and below that for the bandwidth. So yeah, it's not just 2.4 gigahertz, but it's like the entire 2.4 gigahertz range that Wi-Fi uses. Okay. Yeah, you don't want interference. Key point there. So there's Wi-Fi 5 gigahertz. Yeah, it also operates on 5 gigahertz. With 5 gigahertz, there's different bandwidths that are available. So not just 20 megahertz, but you can also do 10, 40, 80, 160. So that means that you can transmit a lot more data at the same time. And it's expanding in popularity. As you may have noticed in the past couple of years, a lot more places. I know I live at the Lodge, so the Lodge has a 2.4 gigahertz channel and a 5 gigahertz channel. A lot of places have both of those. Pretty soon they're probably going to start just transferring to 5 gigahertz just because it's faster. Yeah, and it's like a Swiss Army knife. So you have different ranges for different purposes. If you want to study this whole thing a little bit more, feel free to. I'm not going to talk through it that much, other than it works for an entire 5 gigahertz range. So, like for 2.4 gigahertz, it's like the whole range is like I don't know, whatever 13 times 20 plus a little bit more is. That's the entire range. Versus this, it's like all of 5 gigahertz. So it's from 5 gigahertz all the way up to 6 gigahertz. So it's an entire gigahertz that's used specifically. Oh boy. He's awesome. All right, we're back. Okay, we're back in business. Let's do this thing. What was I talking about? Oh yeah, 5 gigahertz. So yeah, it expands in popularity. More places are using it now. You can transmit more data. It's like a Swiss Army knife. Okay, so encryption and authentication. So there's really like two main families of standards. So there's WEP, WPA. WEP is wired equivalent privacy. WPA, Wi-Fi protected access. And there's 3 versions of it. And if you're interested, how many places have each of those implemented, you can figure that out on wiggle.net, and all of this is like crowdsourced from war driving, and I'll talk about that later. But the important part for right now is that WPA2 has the vast majority of Wi-Fi networks, and it probably has a large portion of these unknown networks as well. So like 75% of all networks use WPA2. It changed actually a fair bit since the last time that we did the presentation. So WPA3 is definitely going up in its share of all of the wireless access points, and then WPA2 is pretty much staying steady, and then WPA, WEP, the more like the worse encryption standards are going down in popularity, which is good. We like to see that. And if you're interested, WEP started in 1999, 2003, WPA was hastily pushed because WEP sucks. And then WPA2 implements WPA, which with like minimal changes. It's just like it uses AES mainly instead for its encryption standard instead of something called TKIP, because AES is way better and way more efficient. So then finally, in 2018, WPA3 was introduced, and that's why it is getting slowly adopted, but that's why such a small portion of access points actually use WPA3, even though WPA3 is really good. So, types of frames, fun stuff. So you have management, control, and data. So for management frames, that's like you joining or leaving a network, so you're sending authentication frames or deauthentication frames. So also probing, associating, roaming, disconnecting. All of those things are management frames. So I don't know if you know this, but say your phone, you have your phone on, it's always going to be trying to find a more, like a stronger signal. So it's always going to be sending out, like probing, sending those management frames out to other wireless access points or receiving them. And it'll connect to whichever one is strongest. So that is what happens on like large enterprise networks even more, like with EDU roam. So if your phone sees like an EDU roam router, it's already authenticated to EDU roam, so it just has to use that authentication key to authenticate with the router, and it knows whichever one is strongest based off of the router probing for new users, saying, hey, this is how strong the signal is between my access point and you. So if it's stronger, your phone will generally connect, if it's on the same network specifically. So then there's also control for reliability. I'm not going to talk too much about that. It's just like acknowledgement, making sure that data gets there. It's not like Wi-Fi frames aren't like they can be lost, but acknowledgements helps that from not becoming a major problem. So yeah, finally, data. Everybody understands data. It's just, yeah, not really more to say. So let's start with WEP. This thing sucks. I hate WEP. Yeah. You know, in 1997, they thought, you know what would be a good idea? Use a 40-bit key for all of our encryption. And as I mentioned before, you're pretty much broadcasting all of your packets to your nearby area, or your frames, I should say. You're broadcasting all of your frames to the nearby area, and just the router is the only one, or your access point is the only one that's actually receiving those signals and can do anything with it if it's encrypted. So if you're sending a ton of those frames, sure, with WP you have an initialization vector, but if you send a ton of frames, the initialization vector is just wiped out, and you can just start testing for the key. So you can start comparing each of those, all of them. Like I think you need 5,000 samples, so 5,000 frames in order to actually do a WEP initialization IV attack and get the key, but it's still definitely possible. And if you're just like sniffing traffic off of one host on a network, and you can get that 40-bit key, it's not that hard to like reverse engineer the RC4 encryption algorithm, because it really just uses, like the main point of this is just an XOR, and an XOR, as you know, many of you, is just like once you XOR one thing with another thing, you can just reverse it by XORing it again. Yeah. So it has tons of critical vulnerabilities. It allows for passive attacks. If you say you receive 5,000 frames, you can just do like a passive attack on it and just offline it, and then get the key, authenticate yourself to the network. So yeah, it was replaced by WPA in 2003. Yeah. Let's talk about some vulnerabilities. So as I mentioned before, the 40-bit key is too small, and if you have enough frames, you have enough initialization vectors to just start brute forcing it. And also, it reuses some initialization vectors. I mean, you know, the IV is only like 24 bits, so obviously it's going to have to reuse some of them in the same communication. So yeah, replay attacks happen all the time. There's not really that much authentication that is done with it, so you can tamper with packets pretty much all you want. Access points aren't authenticated, so you can just send like deauthentication packets and perform a denial of service attack. There's just so much wrong with it, and if you ever see say you're on an on-site penetration test and you see a WEP network, that's like hitting the gold mine. You're set. You're already in the network. You may as well be. Okay, so WPA2. I skipped over WPA since it's not really used that much, and there's not really any sense in talking about it versus WPA2 since they're so similar. So what did it fix based off of WEP? So it uses a much stronger encryption algorithm, AES, as I mentioned before, and uh, sometimes it uses TKIP, which isn't quite as good, but still miles better than the RC4 encryption algorithm, which I didn't go into it in this presentation too much, but if you just like look up a picture of it, you'll see why it's not very secure, because it's very easy to just reverse engineer and brute force the key. So it now uses a 4-way handshake to authenticate users, which thank God, because if you don't capture that 4-way handshake, it is impossible to decrypt any of those packets, because as it stands right now, AES is like you can't decrypt AES without the key. So the way that you can, actually, I think I have a slide on this. Whatever. The way that you can decrypt it and just get the key off of it is using the 4-way handshake. And if you have that 4-way handshake, that's where they're setting up all of their secret keys. So if you have that, then you can just like start brute forcing. And you have to brute force pretty much every single step, so it takes a little while. But yeah, data frames are now encrypted, but management isn't. So you can still send deauthentication frames, and like you can spoof deauthentication frames. Say, hey, I'm this user. I don't want to be authenticated to your network anymore. And the router just like is like, okay, sounds good to me. And then if you just keep sending those frames, they're not going to be able to re-authenticate ever. Okay. So WPA2 types. There's 2 types of this, as there are with pretty much all of these Wi-Fi standards. There's personal, and then there's enterprise. So personal just uses the Wi-Fi password in order to initialize the key transfer and authenticate users, whereas enterprise actually uses its own server for it. So enterprise is a little bit better, just because you're not using the same key to authenticate almost all users. But still, I mean, you have the 4-way handshake, so it's even though the Wi-Fi password is like it can be weak, you're not going to be able to view all traffic depending on the scheme. Okay. So there's 2. Actually, I'm pretty sure there's 3 kinds. Okay, whatever. There's mainly 2 kinds of WPA keys. So or actually 3. Yeah, I was right. Okay, master keys that are used to generate the temporal keys. Then PTK, pairwise transient key, and as it says, that's what's used to encrypt unicast traffic between the router and the endpoint. So any endpoint is like any user. So you're encrypting traffic between you and the router. That's what that key is used for, and it's exchanged during the 4-way handshake. So then the group temporal key, every endpoint for multicast, also used during the 4-way handshake. So if you want to like multicast, broadcast to a bunch of users on your network, that's when you use the group temporal key. Since you're not going to be able to, since every endpoint has its own PTK, the pairwise key, to communicate with the router, you're not going to be able to broadcast directly to anybody else on the network with that one. Okay, so there's dictionary attacks, deauthentication attacks, crack attack. So key reinstallation, which is the crack attack. And basically, that just means that you change the parameters of the handshake, and then the attacker now has the key, and you don't as the endpoint. Then dictionary attack, if the full handshake is captured, you can just like brute force it and try and guess what the key is. So maybe useful for demos. I don't know. Then there's also deauthentication attacks, so you can send deauth frames to the router. Like I said before, those aren't authenticated. So you can just like spoof a MAC address and then say, hey, I'm this user, deauthenticate me. And the router just is none the wiser, and it will do that. So yeah, WPA3. man, WPA3 is awesome. Finally, guess what? Management frames are encrypted. Oh yeah, super exciting. It overall just like increases security. It has a much more intense handshake. It's no longer four-way, and there's a lot. It's called the Dragonfly handshake, and I think I have a slide on it, so I'll save that for a minute. But there's also some vulnerabilities that people have found in it, but in order to exploit a lot of those vulnerabilities, you need a lot of compute power, and it's just not really worth it. So we're pretty safe for now with WPA3, and more routers should be using it. And plus, I mean, who doesn't love backwards compatibility with WPA2? So, WPA3 modes. Again, personal, enterprise, but they also have open network where it also does encryption, and like anybody can connect to it. But it's like you don't have a password, you don't have a Wi-Fi password, but you still have encryption. It's not as good, obviously. Yeah, James? What? How much aura would you say the Dragonfly handshake gives? The question was, how much aura do you think the Dragonfly handshake gives WPA3? I'd say plus 5,000. Yeah, crazy aura. The four-way handshake is like 1,000, so it's like way better than that. You know what I mean? Because you can't just like brute force the key. At least. Oh, you just okay. All right. I'm trying to. Oh yeah. So yeah, there's also personal, enterprise, open network. Personal enterprise, pretty similar to what I talked about in WPA2, just like how it works. But enterprise right now supports much longer keys. Personal may be moving in that direction, but it only uses AES right now. So the same way that it was in WPA2, but it still uses the Dragonfly handshake, which is awesome. I guess I don't really talk about the Dragonfly handshake, but yeah, just like look it up if you're interested. It's kind of too much to go through right now, just in this short presentation. Okay, so a note on monitor mode. If you want to start tinkering with all of this stuff, and with Wi-Fi specifically, viewing all of those packets, you can get a monitor mode enabled Wi-Fi dongle. And so it's similar to, I like comparing it to the Ethernet promiscuous mode, where with Ethernet promiscuous mode, you're just viewing all of the packets that are being sent along the wire and like through your computer, or like that your computer even has access to. So you're sniffing stuff that isn't really even addressed to you, and you can kind of do that with a monitor mode enabled dongle. So I could sit on the other side of the room, and then I could sniff all of James' packets because he's talking about aura, and I can try to decrypt a lot of his packets. And if he's not using encryption, then I can just view it from the get-go. So yeah, you can also do packet injection with those. So any of those attacks that I talked about before, those pretty much have to be done with a dongle that can be put into monitor mode or like a really advanced SDR. But a dongle mode enabled, or a monitor mode enabled dongle is definitely the easiest way of doing that. So yeah, I have 3 up here that we'll be using for demos. So there's only like a few specific Wi-Fi chipsets that actually have monitor mode support, and all of the ones that I could find are right there. Also some RTL 8812BU chips, not listed up here, but this one is that specific chip, and it also works. So pretty cool. And it allows dongles to sniff Wi-Fi traffic, specifically not addressed to it. Packet injection, so you can send deauthentication packets, might be useful. And you can, it also It works only on specific chipsets. So don't expect your random dongle or your like laptop integrated chip to actually work with this. War driving. Woo! Yeah, so war driving, you just have a bunch of these dongles pretty much, and it just in a box. People call it the spooky box, and you just drive around and collect data off of access points that are transmitting around you. So you can get the SSID, so just like the name of anytime you're trying to connect to a Wi-Fi network, the SSID is just what you would think of as the name of the network. And then there's encryption, location. A lot of people like to triangulate the location. Not entirely necessary, but it's still pretty cool when you do it. Then there's also, you can see what kind of encryption, so WEP, WPA, WPA2, WPA3, or no encryption. And that's how I got that graph from a couple of slides ago. So yeah, where are certain networks, you can use like this information for OSINT. You can just like look up what on, actually, sweet beacon, yeah, none of that's that important. Well, you can look up all of that on wiggle.net. So wiggle.net is just like this crowdsourced huge data set of all access points. Like just a crazy amount of access points that are all across the US and even the world. So that map, bottom left, shows the density of all of the access points. So as you can see, war driving is more popular on the East Coast because I don't think places on the West Coast are really that much less densely populated. It's just picked up more over here. And as you can see, between those two like tables on the left, that the one on the left, it was last year's, so it was in Braden's presentation, and the one on the right is, you know, the one that I took a couple of days ago. So as you can see, more people are adopting WPA3, which is great. WPA2 really hasn't changed, and WPA and WEP, the share of the market is going down, which you'll love to see it. And yeah, so you can just like zoom in on that map, see in your specific area what kind of wireless access points there are. You can even find like what encryption standards they're using as well. It's pretty cool. So, Kismet and other Wi-Fi tools. So AirCrack NG is a suite of tools that you can use in order to send spoof packets. You can capture packets in like similar to promiscuous mode. You can see, or you can capture frames similar to promiscuous mode. You can set your chip into monitor mode. You can do all sorts of things. And then Kismet, it captures handshakes and fingerprints. And then all of that data that I mentioned for war driving was probably captured from Kismet, since Kismet just like pipes directly into wiggle.net. So you can see they have a really good interface, and you can see a lot of stuff in it. Then Wireshark, you can also use to like see traffic in specific streams. You can use Wireshark to decrypt packets if you have the Wi-Fi key, and then some other ones for like Wi-Fi Fisher, Armageddon, you can use for evil twin attacks. And I guess I should also mention what an evil twin attack is. So an evil twin attack is a attack where you have two wireless access points, really one target one. So say you have one target access point that's across the room, and there's a host connected to it that you want to connect to you. So, and you want to see all of their traffic. So you can spoof a access point to look identical to the one across the room, but just have a stronger signal, and then de-authenticate the user from the first one, and then it'll authenticate to you, and then it'll send all of the traffic through you. Pretty cool stuff. So if you know anything about like what a Wi-Fi pineapple is, that's pretty much all it does. So yeah, that's what Kismet looks like. As you can see, you have the cryptography standard, the type of network, whether it's enterprise or if it's personal, when it was last seen, what channel it's transmitting on, its BSSID, and the amount of traffic that's being sent through it. So yeah, pretty cool stuff. This is what I'm going to have up for Imagine RIT and tomorrow when we're doing one of the open houses. Really fun thing to talk about. Okay. Any questions? That was a lot of stuff. And always only attack stuff that you own or the club owns that, you know, you have access to. Don't just like go attacking club stuff for no reason. But, you know, like talk to Will, talk to me, talk to like the leads of interest groups if you want to try and hack something, or head of research since it's technically research. So yeah. Any questions? Yeah, Kyle.
Where is the most odd place that you've ever war driven?
I have not gone war driving myself. So like any more than just like using Kismet in my room. Hey Jack.
Yeah.
What is the weirdest place that you've war driven?
We attempted to war drive it in Rochester, but the box didn't work properly, so it never worked.
Oh man, that stinks.
Yeah.
Wow. Jack said that he attempted to war drive in Rochester, but the box didn't work properly. Man. Well, that stinks. Maybe we should get an interest group going. Or a mentorship group, I should say. Oh, yeah. Okay. Any other questions? Any other questions? All right. Yeah, Leah?
Let's say that you had a lot of notes written down on paper about war driving
Okay.
and wireless.
Yeah.
Where would you say that you would keep those notes?
Well, I'd have to say a RITSEC Padfolio.
Outstanding presentation.
Yay! Thank you. Hey, everyone. Education's over. You know what time it is. It's demo time. Okay. So, there are, I think I'll drop